Let us start this lecture with a thought process by Swami Vivekananda, who says expansion is life, contraction is death. All of us want to ourselves such that we can achieve excellence in life, but most of them won't succeed in doing that. Therefore, we must strive to have a expansion in to experience expansion in life. In the last lecture, we discussed about how to reach an orbit. That means, what is the requisite velocity is to be imparted to the vehicle such that it can reach certain orbit. And we learned that we need to not only have a orbital velocity, but also give a total velocity such that it can achieve certain orbital velocity at a particular path. And later on we also learned how to escape the gravitational pull of a planet or the earth, and it is important to provide certain amount of energy such that the satellite can acquire the escape velocity, and we have also derived a relationship for the escape velocity such that a satellite or a vehicle can escape from the gravitational pull of the planet. And having said that, today we will be discussing about interplanetary transfer orbit, and all of us might be aware that in modern time several agencies of various countries they have conducted several interplanetary flight using various transfer path, and it is very important to have that, so that you will be using the minimum amount of energy to have an interplanetary flight between the earth and to the moon or to the Mars. And recently we are having both the moon mission, that we call it Chandrayaan in India, and also the Mars mission. And generally the interplanetary missions being restricted to the solar system, but however in future we may venture into other planets beyond the solar system. And for that let us see that what kind of rocket vehicle you should have such that you can use minimum amount of the energy to have a interplanetary flight. So, for that let us consider this is your planet, it can be earth, it can be moon, and let us say this is an orbit on which you will have to place a satellite, and that is known as parking orbit. And let us say this is your satellite. And now, if the satellite has to be taken from this parking orbit to another orbit, let us say this is your orbit, then you will have to impart certain velocity with this so that it can have a way. That means, you should impart certain amount of thrust, it can change this thing and go to a path. Now, question arises, you may not have sufficient energy to have that. So, therefore, you should use the minimum amount of energy so that it can be going towards the other higher orbits. And this idea is basically came to the German scientist Hohmann, who find that if it can take a elliptical path, it can really use the minimum amount of energy. And that is, let us say if you want to have a satellite from here, and from this satellite from the parking orbit to the other outer orbit, then you will have to go by this path, and this path is basically corresponding to the minimum amount of energy. Therefore, we call it as a Hohmann orbit, and this is elliptical in nature. So, this is elliptical in nature. So, therefore, this is being considered to be the ideal one, but however, it takes a lot of time, this one known as Hohmann's transfer orbit path. Take less time, then you will have to spend more amount of energy and impart higher thrust to the satellite vehicle, so that it can go, and this is basically known as high energy path or the fast path. And in practice people do use it, but however, it requires a large amount of the energy to be with the rocket vehicle. If one wants to use the Hohmann transfer orbit, then the time required to travel from the Earth's surface to the moon will be around 116 hours. But if one wants to travel from the Earth's surface to the Mars using the Hohmann's orbit, then it will take something 259 days. So, therefore, it is basically will be taking a lot of time, and that is the reason why people provide a little higher amount of energy, such that the faster transfer can take place between the parking orbit and also the next or the outer orbit. And these Hohmann orbits are also being used for placing the satellite on the geostationary orbit. Let us look at how it is happening, that we can say, let us say this is your planet or the earth, and this is your satellite, and it is if you look at, like, it can be a satellite can be launched from somewhere, let us say here, and can be placed in this place, and this is your perigee, and perigee will be having a very high velocity Vp, and then it will be getting into the apogee, that is known as apogee, this portion. So, this is having a Va, and let us say satellite is moving with these velocities, but it has not really achieved certain amount of velocity, so that it can move around the geostationary orbit. In other words, this satellite velocity is much lower than the orbital velocity, which is required for the satellite to move around the geostationary orbit. Then one has to do that, you will have to impart more thrust on this apogee, because you will have to give little lower thrust or the lower energy you will have to utilize, so that in the next burn, like, it will be moving into another elliptical orbits, and this is your, you can say, as basically fast burn. And then when it will go again, you will go to the, whenever it will go to this apogee point, then you will have to impart a certain higher velocity incremental way, so that you can get another orbit. This is your second burn, you will have to give little more. That means, this velocity is basically goes on increasing. That means, this velocity is goes on increasing with the burn, and you can go for again another burn, then it will go to another level. So, this is your third burn, and then once you give this again more, then it will go to the, finally it will achieve the orbital level. This be A, the, you can say, A in the fourth is equal to V orbital velocity with geostationary, it can really get the into the geostationary orbit. However, if you want to accelerate this process, it will take a lot of time of getting this, as your vehicle is not having adequate thrust to impart to that. Then if you are having that, let us say for example, you can give a velocity of very high velocity, because you will have to impart to the perigee, that will very high velocities V p, so that what will happen, it will be transferred to another orbit, or it can go to here orbit, like kind of things, right. It can go to another orbit, so that you can achieve very easily. And this kind of path is known as bi-elliptic path. That means you are imparting here at the apogee your thrust, and also you are importing at the perigee, this is your perigee, and such that this is known as bi-elliptic orbit, and which is also being used to accelerate transfer path or transfer from one level to another outer orbit. So, there are various transfer paths can be devised and designed depending on the amount of energy available in your vehicle. Therefore, one has to look at what vehicle you will be designing, and that depends on the kind of propellant being used, kind of engine being used. So, that will be so that you can have that. So, let us look at how can we be reaching out the orbit. We are discussing that, and as we have learned that lowest altitude from the earth where a stable orbit can be maintained is basically an altitude of 185 kilometer, which requires an orbital velocity approximately 7695 meter per second. That means, it is around something 7.7 kilometer per second, that is the required. And to reach this orbital velocity, the requisite ideal velocity to provided by rocket engine is 7,915 meter per second. And here we are not considering the other effects like drag and other things. So, and the velocity loss due to gravitational pull of the earth is around something 450 meter per second, plus the drag losses can be 1600 meter second. Then actual requisite velocity would be something 9515 meter per second. And if you use the best engine that we will be discussing little later on, that is the cryogenic liquid hydrogen, liquid oxygen rocket engine with mass ratio of 9.7, and in which one can achieve specific impulse of 400 second, it can produce ideal incremental velocity of 8916 meter per second. That means, even with the best engine, we cannot really send the satellite to the stable orbit from the earth surface, that is 185 kilometer from the earth surface. So, hence it is difficult to place a satellite even at 185 kilometer orbit. Then with current technology and propellant, a single stage rocket to stable orbit is still not possible, that you can see from this discussion. Now, what we will do that, we will take an example and look at how to basically calculate these orbital velocities, and how to calculate the requirement in the change in incremental velocity. So, approximate velocity increment for typical mission will be basically, if you look at lower earth orbit around 400 kilometer, the actual velocity will be 9.1 meter per second, and the geosynchronous orbit you will be getting around 12.5 centimeter per second, and earth escape velocity we have seen, that is 11.2 kilometer per second. Then actual, and this is the ideal velocity increment for the earth escape velocity is 11.2 kilometer per second, and for actual one will be 12.9 kilometer per second. As I told, there will be losses, and low lunar orbit should have 12.7 kilometer per second if you consider the ideal case, but the real case will be 14.3 kilometer per second. And if you want to land because you need to have certain kind of velocity level, velocity increment, that is something around 13.1 under ideal condition. For actual condition will be 15.2, and lunar soft landing and the return to earth, of course, the ideal is little bit higher than the actual one, because you will be using certain things of gravitational pull when you are landing back, and that will be, therefore, it is actual will be lower. Whereas, when a soft landing you need around 22 kilometer per second, and when a soft landing actual one will be 25 kilometer per second. So, Mars soft landing will need something around 20 kilometer per second. So, if you look at the velocity increment, it is very difficult to get in actual situation. So, now what is the solution, how to go about it, that we will see, and in the next lecture, and we will be considering an example. Now, a question is what is the way out for the space travel, that we will be discussing in the next lecture, and we will be looking at now an example. It is a very simple example. We are considering single stage chemical rocket with ISP of 250 second, that is your is designed to escape off with the following mass, that is payload mass is 200 kg, structural mass is 800 kg, and total mass is 30,000 kg. We will determine the mass ratio, that is your mr, and velocity increment delta v, and propellant payload fraction, structural fraction for this rocket engine, assuming no drag and gravity effects, but in real situation we will have to basically look at consider the drag and gravity effect. So, if you look at the given, this is ml is 2000 kg, ms is 800 kg, m naught is 30,000 kg, and the ISP is 250 second. To find, basically we will have to find out mass ratio, we will have to find out delta V, we will have to find out propellant fraction and structural fraction. So, if you look at, we know that the burnt out mass payload plus structural mass. So, that will be 200 plus 800 is 10,000 kg, and we need to find out the mass ratio. The mass ratio mr is equal to basically m naught by mb, that is 30,000 divided by 1000 is equal to 30. It is a very high mass ratio if you look at that way. So, we need to find out propellant fraction. So, propellant fraction you can get, that is Pf is equal to 1 minus divided by mr, that happens to be 1 minus 1 by 30 is equal to 0.966, which is implies, that is the structural mass, like if you look at the SF plus LF, this is your payload fraction, and this is your structural fraction, is equal to 1 minus Pf, that is coming around something 0.0333 is equal to basically 3.33%. That means you are providing around 3.33% for structural mass and payload mass, which is very difficult to really have that. And of course, we will have to find out also the payload fraction, that is we can very easily find out LF. The LF is L divided by m naught, that is 200 divided by 30,000. I will be getting something 0.0066, and that means LF is basically 0.66 percentage. And what it indicates, that means you are providing the 0.66 percentage for the payload, and the structural fraction will be ms divided by m naught. You can also get from here, right, because already you know this LF. So, you can find out structural fraction from this, or you can find out directly. So, that is 800 divided by 30,000 is equal to 0.0266, implies that SF is equal to 2.66 percentage, that is your structural fraction. So, we need to also find out the change in the velocity, that is delta V. Delta V is nothing but your ISP Z naught ln mr. So, you will find out this is 250 into 9.81 ln of 30, that is 8.2 kilometer per second. You see that it is a very small velocity to really, even you cannot escape with this velocity, and keeping in mind mass ratio is quite high, and the payload what is carrying is very small. That means it is a very gigantic engine, and it is having a mass of 30,000, it is only taking the payload of 200 kg. So, then question arises, what is to be done, and that we will discuss in the next lecture. Thank you very much.